I've got the first part of the Chapter 8 review videos going up, the packet's up. I'll have the problems posted. I got to run back to my office after class and finish uploading the videos. But there's two things in Chapter 8 that like I want to go over, just kind of like yesterday, how we kind of like talked about why we do the rotational stuff. There's one thing in Chapter 8 that like I get lots and lots of questions on, and I didn't want to waste a ton of time in the review video doing it, but I just wanted to show you where, when we go to do the trig substitution, it tends to kind of confuse people kind of as like to the why we're doing it and what to do with these radicals. Everybody tends to kind of do a little bit too much work when they're setting them up. So the reason that I left the trig, so in Chapter 8, you have to learn integration by parts, right, which tells you how to split, you'll see it tells you how to split an integral up into pieces when you have two functions of x being multiplied together, right? You just can't separate them and you can't integrate it directly. So there's a very systematic approach to that. Then the second section, we talk about trig integrals, right, and how to deal with integrals where you have combinations of trig functions. The third section, though, is trigonometric substitution, and that's one of those sections that some people are like, you can dump, but if you are going on to Calc 3, the reason that I don't want to leave that out is because you're going to be working in multiple coordinate systems in Calc 3. You're going to go cylindrical, spherical, so you really need to know how to deal with trig integrals, but more importantly, you need to understand the concept of how are you going to translate something from the current variables you're working with into a new variable to make your life easier, not harder. So I want to kind of go over very briefly where these radicals come from and why we're able to do this, and so you kind of take some of the mystery away, because it just looks like a bunch of stuff you have to memorize, and like I didn't really get it either. So if you kind of look back, right, and think about the Pythagorean theorem, and you're going to find, if you actually pay attention in Calc 2, the Pythagorean theorem comes up like a lot. It is the root of like a lot of stuff we look at. But if you look at just kind of the most basic form that you guys are used to dealing with, right, you have a right triangle, and we would say, well, what the Pythagorean theorem does for you is it says that if you square the legs and sum them up, it equals the square of the hypotenuse. So if you're solving for one of the sides of one of these triangles, you see a couple of things happen. If you want to solve for C, right, then all you have to do is take the square root of both sides of the equation, right? And notice when you're solving for the hypotenuse, right, what's inside the radical is a plus sign, okay? Because that's how you can always tell if you're looking at one of these radicals and you see a plus sign, you know that is in fact the hypotenuse, okay? But if you want to solve for one of the legs, so let's say you want to solve for A, well then A squared, right, is going to end up being C squared minus B squared, and when you take the square root, right, you'll get side A, right? And notice that the hypotenuse is always the first term in the radical, because you had to move that other leg over to the other side in order to take the square root to get A by itself. Similarly, if we solve for B, right, you would subtract A squared from both sides, then take the square root, right, and that would give you the other leg. But once again, notice that the hypotenuse is what's first. So when you're doing trig substitution, what it's going to do is it's going to let you integrate integrals that involve radicals where maybe u substitution isn't on the table, because that's usually our go-to when you see a radical. You want to try to u sub what's under the radical, but you may not have the du elements you need to solve. So what we can actually do is we can translate this from variable x into variable theta using a triangle. So there are going to be three forms of the radical you're going to see. You're going to see the sum of two things, or you're going to see two different difference of squares under the radical. So I just want to kind of show you for a minute kind of where this comes from, and if you have to do a little logical deduction, you can kind of see this is all just an extension of the Pythagorean theorem. So if you have a radical of the form, right, a squared minus u squared, a is going to represent a constant number, and u is going to be a variable expression of x. So it could just be x, like you could have something like 4 minus x squared. Well, then if it's 4 minus x squared, right, then your a was 2 because it's 2 squared minus x squared, right? But if you want to actually draw the triangle that this is representing, the convention we use, right, is the following. We tend to always draw the triangle like this, and we typically let theta be that lower left angle. So if we look at the structure of the radical, right, this is just somebody solving for one of the sides of a triangle. So when you see the minus sign here, you know that A represents the hypotenuse. So that means the length of the hypotenuse is going to be A. Then if the legs, right, are going to be, one of them is going to be U, right? We've already used A. So if we have the legs left, right, one of them has to be the radical itself because this represents a side. That's how we got from the Pythagorean theorem. And the other is going to be the expression of U. So if A is still on the table when you're trying to write the legs, we typically put A on the base. But since we've already used A, U is going to be the height. And what this person did, right, the general form is they solved for the radical, which was solving for the base, okay? So there is more than one way to envision the triangle, but this is kind of the default setting that most people use. So if you wanted to look at a radical and, or excuse me, an integral and translate this into an expression in terms of theta, well, if you look at this, the radical, right, is the base, and the whole idea is to replace that. So look at the other two sides, right, that don't involve the radical with respect to theta. Well, it's the opposite side, and it's the adjacent side. So sine of theta is going to be u over a. So when you solve for that, for u, we say, well, u is a sine theta. So we're sort of like making a u substitution. So then you need to have a du, right? And your du would be a cosine theta. You just take the derivative like we would, and then you'd have d theta, right? And then we would want to replace the radical itself. So the radical itself, you do not have to do this math on a problem. I'm going to show you where it comes from, and I will allow you to just recognize where the radical should come from. So what's going to happen under that radical, if you substitute these elements inside the radical, it's going to turn into a Pythagorean identity. So if you look at a squared minus u squared, and I replace I replace u with a sine theta, now our expression becomes a squared sine squared theta. You can factor the a out front. And what's 1 minus sine squared? Cosine squared. It's like the most famous Pythagorean identity and trig, right? So now this is just a cosine squared theta. So if you take the square root of both sides, the radical just becomes a cosine theta. So what will happen inside these radicals when you actually make this substitution using your triangle is the Pythagorean identity will always kick in, and there's two Pythagorean identities that we use. We use sine squared theta, right, plus cosine squared theta equals 1, and then we use secant squared theta plus 1. Wait, I think I might have this backwards. Yep, my bad. I always get this one backwards. Okay. Secant squared equals tangent theta, or tangent squared plus 1. So if you just look at the structure of these, and you'll see in the trig section, we look at integrals involving sine and cosine because their derivatives go back and forth, right? And we look at integrals using secant and tangent because their derivatives go back and forth. So the derivative of tangent is secant squared, right? The derivative of secant is secant tangent. So you'll always see sines and cosines get paired together and secant and tangents get paired together. So if a Pythagorean identity kicks in and you plug in a u into this radical, cosine should come out. That should make sense because you just make the substitution and this lets you, if you rearrange it, turn cosines into sines and sines into cosine. Similarly, if we decide to use secant as our u value, well then the integral will turn secant into tangent. If you let tangent be your u, and I'll show you those triangles, when you throw it into the radical, this will turn tangents into secants. So it should never be a mystery of what the radical is going to become once you identify what your u is, and you can always figure that out by the two sides that aren't the radical, well then the radical needs to then spit back out cosine based on that identity. So this is going to happen inside that radical every single time. So I don't expect you to work it all out, but if you just for some reason can't remember, you can do the derivation fairly quickly. So let me show you an example of an actual problem of where we would set this up, okay? And I'm going to try to do one different from the review packet just so you can see something like this. So if you have the integral of 4 over x squared times the square root of 16 minus x squared. This is not an integral you could do by any traditional method. If you tried to u sub it, your u would be 16 minus x squared, and then your du would be negative 2x. You don't have any x's in the numerator, and moreover, you have 2 extra x's in the denominator. So trig substitution is going to be the best way to try to do this, okay? So what we would do here is you always look at the radical. The structure of the radical is telling you how to set up your substitution. So this is in fact an a squared minus u squared situation. Your a is 4, right, because of this 16, not because of the 4 in the numerator, and your u is x. So when you set up your triangle, right, we can see here that this is the hypotenuse, so that means the hypotenuse is 4. The radical itself, right, is going to go on the base, and the height is just x. So for your substitution, we're going to say, well, x is 4 sine theta. The reason I have to take the derivative, right, is just like when you sub, I have to replace the dx. So dx is 4 cosine theta, and the radical itself, since x was 4 sine theta, when I plug in and do the Pythagorean theorem, 4 cosine theta comes out. Oh, and don't forget your d theta there, like I just did. So once you have those three things, once you've identified what x is, what dx is, and what the radical is, you literally just translate the integral into your new variable. So if I come back here, the 4 stays where it is, but I have an x squared. But x is this, right? So if I square it, I'll replace x squared with 16 sine squared theta. The radical is 4 cosine theta. And then I have to deal with my dx, and my dx was also 4 cosine theta d theta. So once you've translated all the elements into theta, you then simplify everything down and you integrate. And this stuff is always supposed to get easier, not harder. Okay? Question? Yeah.
And then how'd you dx then?
I just took the derivative of x. Yep. Once you've decided what x equals, you just take the derivative and that gives you dx. Uh-huh.
Will dx and the square root always be the same?
No.
No.
No. In this setup, yes, because sine turns into cosine because of the radical, and the derivative of sine is cosine. So for this particular setup, yes, but that will not be the case at all in the secant tangent world. So, but yeah. So what happens here, the 4 cosine theta in the denominator cancels the 4 cosine theta in the numerator. I can cancel a 4 out of my 16, so I'll just bring that 1/4 out front. And now what I'm left with is 1/4 over 1 minus sine squared theta d theta. Well, I can't really integrate that directly, but what's 1 over sine? So for the reciprocal identities, you can always remember them because the s's and the c's go together. So if you flip sine, it's cosecant. If you flip cosine, you get secant. So the s's and the c's always pair up. So this is actually the integral of cosecant squared d theta. And remember, secant squared and cosecant squared are known derivatives. So this is the derivative of negative cotangent. So now you can just integrate this directly, and you get negative 1/4 cotangent theta plus c. But your answer isn't complete because nobody cared about theta. So this is just an intermediary step so we can get through the integration. But your final answer needs to be in terms of x, and this is why you draw the triangle. So if you've done your triangle, you can translate any of these trig functions right back into x just simply using your triangle. So cotangent is 1 over tangent. So if tangent is opposite over adjacent, then cotangent is adjacent over opposite. So your final answer just ends up being negative 1/4. The adjacent side to theta was the radical, and the opposite side was x. And so there's the answer to the original problem. So when you get into Calc 3 and you start doing spherical, rectangular, polar coordinates, you're going to be translating things from x, y, or x, y, z into functions of theta and r and phi. And so when you get into spherical, I can't say words today, spherical and cylindrical coordinates, there will be trigonometry involved in that. And so you just need to kind of get into the habit, or at least see up front what it looks like, because you can just translate it into another variable and then go back to x at the end. So this is sort of like a really elaborate form of a U substitution, right? But because of the structure of these radicals, we know we can always set up a right triangle because they're just results of the Pythagorean theorem. All right, so let me show you the other two forms. Okay. So we saw that when you see a plus sign, right, under that radical, that means someone solved for the hypotenuse. So if you're setting up the triangle, these are always the easiest ones for me to remember, right? If you're setting up the triangle, theta's still in the lower left corner, but the radical itself, right, has to be the hypotenuse. So that means the two remaining sides are either A or U. And what we like to do is, A is a constant. We usually like, if the constant's available, we usually just put the constant on the base. So by process of elimination, the height's got to be U. So if you want to know what to call U in this sense, well, remember said, look at the two sides that aren't the radical. So the two sides you have left over to work with are opposite over adjacent, right? So that's going to be tangent. So U is a tan theta. Your du is a secant squared theta, d theta. But the radical, right, well, because of the Pythagorean identity, and I'll work it out for you so you can see it, but when we work out the Pythagorean identity, you're going to see it's just going to come out to be a secant, because that's what that Pythagorean identity does. It lets you convert tangents into secants and secants into tangent. So if we put tangent in this radical, so if I replace u with a tan, and we square it, right, then just like before, I can factor the a squared out front. I get 1 plus tangent squared theta, and 1 plus tangent squared is secant squared. So this guy just works out to be a secant theta. So I don't need to see all of that algebra every single problem. You should know that if sine goes into the radical, cosine comes out because of the Pythagorean identity. If tangent goes into the radical, secant's going to come out, right? And then the last one you'll see, we're going to throw secant into the radical and tangent will come out. So you can see here the dx and the radical did not match at all, right? So you have to be real, real careful. So let's look at one involving this with real numbers, just so you can kind of see how this applies. So let's look at something like this. Oh, this is actually 9x cubed. And really, this is just a game in the radical of pluses and minuses. And what's going to matter is whether the constant's up front or the expression's up front. So once again, we look at the radical. I see a plus sign under that radical. So if I want to draw the triangle, well, the radical is the hypotenuse. So that's going to go there. What's my constant A in this guy? 1, because it's a squared plus u squared, right? So a is just 1, so a goes on the base, and x goes on the height. So x will be just 1 times tan theta. Dx will be secant squared theta d theta, and the radical itself will just be 1 secant theta. So once you understand this structure, if there's a pattern that's emerging and you don't really have to do, it's not like a ton of work, but everybody always tries to do everything from first principles on these problems, and it's not really necessary. So now all I have to do is translate my radical, or my integral, excuse me, into these new elements. So in the numerator, the 9 stays where it is, but I have an x cubed. So I come over here to my x expression, and I cube both sides. So this will be x tangent cubed theta. The denominator is just the radical, so that's just secant theta. And then don't forget about the dx. The dx gets replaced with secant squared theta d theta. So then, hopefully it simplifies into something a little easier to solve. And I can cancel a secant theta with a secant theta. So now all I have to integrate is 9 tangent cubed secant theta d theta. So if we want to integrate this, well, I need to have a derivative in there, okay? So there are only 2 known derivatives for trig functions that involve secant and tangent. One is secant squared, that's the derivative of tangent, but I only have 1 secant left, so that's not going to work. And the other one is secant tangent, and that's the derivative of secant. So if I take one of those tangents, right, and pull it to the side, well, there's my secant tangent, right? So let's see what happens if we factor that out. So I'll get 9 tangent squared theta, right? And then I'm borrowed one of the tangents. So what I did this for is, if you look right here, right, well, this is the known derivative of some other function, and that other function just happens to be secant. But I don't have any more secants, right? I've got a tangent squared. So what I can do is, anytime you have even powers of cosine, sine, secant, or tangent, you can use their Pythagorean identity to convert them into the one you want. So all I have to do is make a substitution, and I can turn those tangent squareds into secants. And now I'll have u can be secant, and du can be secant tangent, right? Because that's the whole idea. You want to be able to u sub as many of these guys as we can. So the Pythagorean identity says replace tangent squared with secant squared minus 1. So now what I have is, I have to say, well, if I let u be secant theta, then my du is secant theta tan theta du. So my integral would just become 9 times u squared minus 1 du. And that's a very easy integral to integrate. And in the chapter 8 section, I do a bunch of, or the trig integration section, I do a bunch of examples, and I've actually typed out the guidelines for you that kind of show you when to factor things out and what to do. And we do a bunch of examples. So if we anti-differentiate this, we get 9 times u cubed over 3, right, minus u plus c. So now I have to plug back in what u was. So I get 9 secant cubed theta, right, over 3, minus 9 secant theta plus c. So this was a double substitution problem. We had to turn everything into theta so we could get rid of the integral. We had to use a u substitution to integrate our resulting angle, but I'm still not done because my final answer has to be in terms of x. So if you go back up, before you check your triangle, look at what trig function is in your answer and look at your little list you made right here and scan it. Well, there's secant right there. We actually see secant is just the radical itself. So I can come back down here and say, well, my final answer in terms of x, 9 divided by 3 is 3. Then I have my radical, 1 plus x squared, that's secant cubed, minus 9 root 1 plus x squared plus c.
So if the if the trig identities in the answer weren't originally in the triangle, would it up there?
Well, if it wasn't on the list of things you listed out, you can always get it from the triangle because we have all 3 sides on our triangle, so you can find all 6 trig functions based on the triangle. And so secant is 1 over cosine, right, which is adjacent over hypotenuse, so you would just do hypotenuse over adjacent. You would just flip it. And so those reciprocal identities you guys are supposed to know from trig, and the way I remember it, everybody remembers cotangent and tangent. That's a kind of easy one to remember because they both have tangent in them, right? But secant goes with cosine, and sine goes with cosecant because I always remember because the s's and the c's go together. They always stay together. So a sine turns into a cosecant when you flip it, and a cosine turns into a secant when you flip it. Also, if you ever pay attention, any trig function that starts with the letter c, its derivative is negative. And that's true for the arc tangent, like arc sine, or arc cosine, arc cosecant, arc cotangent. Their derivatives are negative. The derivative of cosine is negative sine. The derivative of cosecant is negative cosecant cotangent, and the derivative of cotangent is negative cosecant squared. So all the ones that start with the letter C all have negative derivatives. So there's a lot of patterns in trigonometry, and because every time you learn something trig related, you kind of in theory have to learn it 6 times because you have 6 trig functions. But there's always a pattern, and if you see the pattern, and really all you have to know is the sine cosine rules a lot of times, because if you see the pattern, you can easily work off the pattern to translate everything back. All right, so the third radical that you'll see, and there's only 3 types, right? The first one we did was the minus case, and that was a squared minus u squared. So the only case we haven't looked at is u squared minus a squared. So if we're setting the triangle up on this one, right, once again, theta's in the lower left corner. So when we're looking at the minus cases, right, the first term in the expression is the hypotenuse. So that means the hypotenuse is length u. All right, why isn't this focusing? There we go. So the only 2 sides I have left to label are a and the radical. So remember, if the constant's available, we like to put it on the bottom. And that means the height of this is the radical itself. So the 2 sides that are left, right, are adjacent over hypotenuse. And it seems really, at first when you do this, it seems like, oh, I should use cosine. Well, if you do use cosine, cosine theta is a over u, but remember the goal is to solve this expression for u, so that would give you u is a over cosine, so u is actually a secant theta, because we want to have it in one line. So here, your u will be a secant theta. Your du is a secant theta tangent theta, because that's the derivative of secant. And the radical, well, if you put secant in, tangent should come out, because once again, the Pythagorean identity would kick in, and so that's all it can do is change secants to tangents and tangents to secant. So once again, you can see your du and your radical do not match. That will only happen with the sine case up front. So let's look at an example of one of these. Oh, here's an interesting one. So I like this one because you don't actually see a radical, right? But when you have a fractional exponent, if the denominator is a 2, that's a square root, okay? So what this is it's the square root of x squared minus 25 cubed, okay? So this is in fact our radical. So it is of the right form. So if we draw our triangle, right, our u in this case is just x. So x is the hypotenuse, a is 5, so then x squared minus 25, right, under square root is the height of our triangle. So x is going to be 5 secant theta. Dx is 5 secant theta tan theta d theta. And the radical is just 5 tan theta. So people, for some reason, drop those constants. And you'll see in a lot of problems, a is 1. But if it's not 1, you've got to be careful not to drop it. Because when they go to plug things in and translate the integral, they'll just drop some like 5s and 4s and make a mistake. Yep.
Isn't secant x over 5? Oh, yeah, never mind.
That's cosine. Yep.
Why did you square the thing in the radical? Or cube?
Why did I cube?
Why isn't it cubed if it was?
Well, we haven't translated the integral yet.
Okay, so does
I'm just dealing with the form of the radical.
Okay.
So what tells you what to do in these problems is simply the stuff inside the radical. That's all you're dealing with first. Then once you have those 3 elements, you go back and you translate what you've got, and then you simplify and do it from there. But yeah, we will cube it when we plug it in. So now when we translate our radical, right, well the first thing I have is x squared, so I'm just going to square my x expression, and that's 25 secant squared theta. Then I have the radical, okay? So remember, the 1/2 goes away. We're just going to cube the radical itself. So if x squared minus 25 under a square root is 5 tan theta, when I cube it, I'm going to get 125 tangent cubed theta. But then I still have my dx, and dx is 5 secant theta tan theta d theta. Oh God, I don't even remember. We didn't have any denominators here to cancel 5s. All right, so I'm just gonna be lazy and put my constants out front. Actually, that's just 125 squared. So I'll just write it as 125 squared, all right? So now we gotta count up how many of these guys we have. So we have 2 secants here. We have another secant here. So that's secant cubed theta. I have 3 tangents plus another tangent. So that's tangent to the 4th d theta. So I've got a secant squared. So I could, because I'm going to have to use sub this again. If I pull out a secant squared, I'm just left with 1 secant. And that means I got to turn everything else into tangent. And I can't turn a single secant into a tangent. I have to have at least 2 of them to use the Pythagorean theorem, right? If I pull a secant out, though, if I pull 1 secant and 1 tangent out, well, then I'm left with secant squared, and I can turn those into tangents, and I can use a u substitution. So what I want to do here is I want to steal one of the secants from up front. So there's my secant squared. I'm going to take one of my tangents, and then I'm going to have secant theta, tan theta, right, as my du, which means my u needs to be secant, and oh no, that's not going to work. Dang it. That's not going to work. Right? You see why it's not going to work? Because I have an odd number of tangents. I can't turn them all into secants. And if we pull out a secant squared, oh, yeah, then I can't pull that secant into tangents. So what you have to do in this situation, there's two possibilities. When you can't do a u sub, meaning a secant squared pulling out doesn't get the job done, and a secant tangent doesn't get the job done, you have two other methods, okay? One is that you borrow a tangent squared, turn it into secant squared plus 1, simplify, and see if you can work it out from there. Another possibility is you rewrite everything in terms of sines and cosines and see if it simplifies from there, because sine cosine integrals are actually easier to solve. So let's try that. So this got us stuck, right? So we can't do that. So let's try rewriting this in terms of sine and cosine and see if that helps us out at all. So I get secant is 1 over cosine cubed theta. Tangent is sine to the 4th over cosine to the 4th d theta. So now when I simplify, it's not 125 degrees, it's 125 squared. I have sine to the 4th theta over cosine to the 7th theta d theta. So I have an odd number of cosines, but it's in the denominator. So this one's going to require like 2 different trig substitutions. So in a normal semester, I just picked this problem at random. In a normal semester, I would go through and show you guys how to work all this out, but like this is going to be well beyond the level of difficulty I'm going to expect you guys to be able to do. But it is a good problem to look at because you can see how kind of crazy these trig integrals can actually get. So the standard, when this method doesn't work, we only have 4 options when you're doing secant tangent integrals. So option 1 was u sub with tangent, that didn't work. Option 2 was u sub with secant, that didn't work. Option 4 is really do sines and cosines, that got us stuck. So then what you do is you pair off a tangent squared, throw in secant squared minus 1, simplify the radical, and then see if you can integrate. If you can't, you have another tangent squared, and you do it again, and you keep simplifying until you can integrate. So this one, unfortunately, is a little bit nasty. So, and I just want to write on here, so no one freaks out on the video. This one's too hard for a test question. It's going to require too much computation. So we'd have to do about another half a page of trigonometry and then go back. But the methodology is sound, right? You label it, you translate it, and then you integrate it. So I always make sure I work out the problems. I'm going to give you guys a much more direct path. But I did want you to at least see an example of a problem where they didn't draw the square root for you. All right. So I'm trying to think of all the sections in this unit. So integration by parts, trig integrals, trig substitution, and then improper integrals. I wanted to maybe talk about those for a second because we did a little bit of it when we did the integral test. Those were improper integrals, but oops, let me go to my other file here. Oh, partial fractions. I wanted to talk about partial fractions. Does anybody have any questions about that stuff, you just got to practice. But on the review packet, I do a bunch of problems, and then and the ones I'm assigning you are way more straightforward. They're like kind of like the first two we did, where it's a real easy out to get out of the integral. I made sure to work them all out in advance. So with partial fractions, the thing that kind of gets people in the weeds is understanding like the algebra steps involved, kind of why do we do things the way that we do. So the first thing you want to do with a partial fraction, right, is you want to factor the denominator completely, okay? So sometimes you'll get a fraction where the denominator is a polynomial and it's clearly not factored and you have to go in and break it up. But sometimes it'll look factored and you still have to check that you can't factor it down further. And so your factorization will always be linear terms or irreducible quadratic terms. So for example, I did a problem on the exam, which a lot of people fell for, where I had things like this. And I think I actually had like an expression up here. All right, so everybody looked at that denominator and they were like, oh, cool, sweet, it's factored. I don't have to do anything, right? It's okay to have quadratics, but the quadratics have to be irreducible. This guy will not factor. You can't factor x squared plus 1, okay? But this will factor. And it factors into x minus 2, x minus 3. So if you rewrite this expression completely factored, what you actually have is x minus 2 squared, x minus 3, x squared plus 1. So what a lot of people got wrong on the exam was they left that quadratic not factored and they didn't realize they actually had an additional x minus 2. And so what partial fractions is actually doing is it's saying this gross disgusting fraction that we want you to integrate is actually the result of adding up other fractions. Like somebody's already added them all up, gotten the common denominator, and simplified it down into this. And so what we want to do is we want to break it up back into simpler fractions so then we can integrate each fraction individually, because you just don't have the tools you need to integrate this way. So what the method of partial fractions does is it wants you to come up with the maximum possible combination of individual pieces that could have been used to add this guy together. And there is kind of a methodology to this. So with linear factors, what's the derivative of a line? It's a constant, right? So if you take the derivative, it's x to the 1, you get a constant. Yeah, question?
Okay, I'm sorry. How is it negative minus 2 and minus 3 and then be minus 6 and minus
Oh, you're right. That should be a plus 6 right there.
Okay, sorry.
That was me, my bad. So I don't make stuff up on the fly, but yes. The first time I wrote a problem like this on the test, my intention was to make the factor do what I did, and I wrote a quadratic that wouldn't factor, or didn't factor the correct way that I wanted it to, and I was so mad. So like when I was grading the test, everybody was doing it right, and I messed up when I wrote the problem, and then this time I was so careful to make sure I did that. But yeah, that's how it's supposed to be. It is definitely supposed to factor like that. Okay. So the derivative of a line is a constant. So the idea here, the reason we want to factor it down completely is you always want to make sure that each of these fractions puts you in a 1 over u situation. Because the antiderivative of 1 over u is just natural log of u. It's really easy to antidifferentiate that. So when we break this up, we say, well, for every linear factor we have, it's some constant number that I don't know over that line. Okay? And then here's where people get confused. X minus 2 squared is, if you FOIL it out, is in fact a quadratic, right? But it's a linear factor. So what you have to do, if it's a repeated linear factor, well, it could have been b over x minus 2, But you also could have had a second fraction that had a denominator of x minus 2 squared. And so when you're looking at these denominators, when we expand this out, their common denominator will end up being that. And so the goal here is we create the maximum number of fractions we can possibly have, and then we solve for those variables in the numerator. And some of them do in fact turn out to be 0. Some of them turn out to not really be there, but you have to at least, make sure you account for all of them. All right, so then the next factor was just x minus 3, so that's still a constant on top. But the last term is a quadratic. So what's the derivative of a quadratic? A line, right? Because every time you take the derivative, you drop a power of the exponent. So the derivative of a quadratic is a line, so I need a line on top. So this is actually EX plus F. If that x plus 1 quantity had been squared, then I would have had another fraction that was gx plus h over that squared. So the way that you deal with the repeated repeated factors is whatever their exponent is in the original denominator, that's how many partial fractions you have to devote for it. So if you look at it, x got 1 fraction, x minus 2 got 2 fractions, x minus 3 only got 1, and x squared plus 1 got 1. Okay? But if I had put a squared on that x plus 1, I would have had to devote 2 fractions to it. So this would be the components of the partial fractions. All right. So I actually want to show you how to do the algebra to actually solve for the variables. We're not going to do this one because it's insane. It's just going to take forever. But this would be an example on an exam where this question was set up but do not evaluate, because the algebra to get through this problem was crazy, but it was really easy to set up the partial fractions, and I was testing people on, do you know how many fractions you need? Do you know how to factor the denominator? So these questions, it's unless they're just overly simplistic, they're kind of hard to work out from start to finish. But there are 2 algebra techniques that you use to work them out that I want to make sure you see. So let me pull up, I got a couple good questions here that I pulled out earlier. Let me go back to my book. Here we go. Partial fractions, there we go. And then I worked through some of these with you as well. And I typed out notes and stuff in the packet. You'll see it when you look at it. All right. So let's look at something like this. Yeah, these two things we're talking about today, these are the 2 sections that I just really feel like you need like a live body in the room so you can like ask questions, because it's not too terrible, but it is a little jarring when you see it for the first time. Okay, so what I want to do before I can even attempt to do this problem is I want to factor that denominator out completely. So rather than just writing the integral again and again, let's just look at the term in the denominator and see what we can do with it. So the first thing that I see is, well, every single term has an x. So we can pull an x out front. And then I have to check, is that quadratic reducible? Well, it is. It's a difference of squares. So the difference of squares, that's going to factor into x plus 2, x minus 2. So that means, I'm going to drop the radical for a minute, the integral for a minute. That means that this fraction we started with is now possibly the sum of 3 linear fractions. So we'll have a over x plus b over x plus 2 plus c over x minus 2. So to solve for a, b, and c, and by the way, what the step I'm about to show you, it's like a nice little algebra hack, will work in any problem that involves fractions and you want to eliminate all the fractions right out of the gate, okay? So what you do is you multiply both sides of the equation by the common denominator. And the advantage in these problems is you'll always know what the common denominator is because it's that right there. It's always, the common denominator is always kind of shown for you out front. That's what we split all this up for. So when you distribute this, you have to do it to both sides of the equation. So all you're going to get left with on the left is the numerator. On the right, when we bring this apart, right, well, the x is going to cancel the x, so you'll get a, right, times x plus 2, x minus 2. The b, the x plus 2 cancels, so you just get x times x minus 2. And for c, the x minus 2 cancels, so you just get x times x plus 2. Right? So the next thing you do, right, in theory, is you're supposed to pick, you have 3 unknowns. You have to find a, b, and c. So you're supposed to pick 3 values of x to plug in to both sides of the equation and get a system of equations and solve, right? But we can do better than that, right? If your factors are linear, which all of ours are, for every linear factor of x, you can strategically pick values that will eliminate variables very quickly for you when you're solving this. So our variables that would have made the denominator 0 would be 0, 2, and negative 2. Does everybody see that? Right? So let's let x equal 0 first. So if x equals 0, well, that's really easy to plug into the left side. You're just left with 12. Well, every one of these terms that has an x attached to it, those are going to go away when you plug in x equals 0. So all you're going to get is a times 2 times negative 2. Because b times 0 was 0 and c times 0 was 0. So if we divide 12 by negative 4, a is negative 3. So you can strategically pick your x values for every linear term. It's going to zero out a bunch of stuff, right? So let's try x equals negative 2. Well, if I plug in negative 2 here, I'm going to get positive 4, right? Minus 24, which is going to give me minus 20, plus 12, that's going to give me negative 8 on the left side. All right, make sure I did that right. 4 minus 24 is negative 20, plus 12 should be negative 8. All right, I'm really bad with arithmetic in my head. All right, so the negative 2 is going to zero out all the x plus 2's. So these two terms are going to wipe out, and you only have to plug negative 2 into the middle part. So you'll get b times negative 2 times negative 4. So you're going to get negative 8 divided by positive 8. So b is negative 1. The last one we have is positive 2. So now I'm going to get 4 plus 24 is 28, plus 12 is 40. And so now every term that had an x minus 2 gets wiped out, and I only have to plug 2 into the last term. So it's c times 2 times 4, and 40 divided by 8 is 5, so c is 5. Did I see how I did that? All right, I'm just making sure because I mess these up a lot. I'm really bad at arithmetic on the fly. All right, okay. So now that we've got our a, b, and c, your new integral is this. A was negative 3, so it's negative 3 over x minus 1 over x plus 2 plus 5 over x minus 2. So integrating this is the same thing as integrating that big ugly fraction we started with. And so the negative 3 is a constant, so the antiderivative, right, of 1 over x is the natural log of x. Then I'll have minus the natural log of x plus 2 plus 5 times the natural log of x minus 2 plus c. And so if you've done the partial fractions right, it's supposed to be making the antidifferentiation a snap. And the reason we didn't have to worry about chain rule or anything like that or use substitution is notice the derivative of all these denominators were 1. So your u sub was really, it was 1 over u, but then your du was 1. So you were just able to go natural log, natural log, natural log all the way across for your linear terms. So when we talked about telescoping series, what we like to do in Unit 3 is I like to give you a series where you've got like n times n plus 1 in the denominator. Those are two linear terms being multiplied together. You can use partial fractions to separate them, and you see that it's usually like 1 over n minus 1 over n plus 1 or something like that, or the other way around, and you see you actually just had a
I
telescoping
found something
series.
on the web about is where you got like 10x1 of the denominator to linear term. Check it out.
Check it out. Thanks, Siri. Yeah, so what I would like to have done is then you just do a two-step partial fraction problem. You turn it into a telescoping series, but you guys just didn't know partial fractions. But the biggest thing that I want you to know is if I want you to work out a partial fraction problem, it will be something very basic like this, where you had linear terms. If I want to actually work it to completion, it's only going to break up into 1 or 2 fractions, or sorry, 2 or 3 fractions. And you see this algebra was actually very quick and not too bad, and then you have to know how to take the integral. If I want you to do something more complicated, what it'll do is it'll be like set up but do not evaluate. But you do need to understand, do you know how many fractions to assign to each denominator factor? Yeah.
Will you like repeat how the rule you said to like how to know?
So it's written in the packet for you.
Okay.
So every section in that packet, I've got notes, diagrams, pictures, and it's all typed out for you in there. And so it actually has a section, it tells linear factors, quadratic factors, and then it shows you, but the way that you know, the quick way that you know, right here, is the exponent attached to the factor tells you how many fractions get devoted to that factor. So that's why this was squared. So we had 2 fractions that involved x minus 2, right? And so that's how you deal with repeated factors. But one of the mistakes people make is they'll see an x squared and they'll think it's a quadratic, and they try to put like an ax plus b on top, and it's like, no, it's a over x plus b over x squared, because it's a linear term quantity squared, not a quadratic. Yeah. But yeah, it's all typed out in those chapter 8 notes for you guys. I was really careful to make sure, and I wrote all the equations needed and all that stuff, because I want you guys to be able to look back on that, because like every single topic in chapter 6 and chapter 8 that I gave you guys in the review, I know for a fact it came up in another course I took after I left Calc 2. So I just want to make sure that you guys have something if you need to go back and reference, because, you know, and even the average Calc 2 student doesn't always remember how to do this stuff. So I just want to, you know, when they leave Calc 2, they don't remember going back to it. So I just wanted to make sure you guys like understood that, and it wasn't just because of your crazy semester. It's, you know, it's just going to happen. But all of this stuff comes back around at some point in some way, shape, or form.